Good morning, everybody. Um, this is my first time streaming, so I hope I've done this right. If anyone's listening on chat, then feel free to say hi and just let me know that you can indeed see me properly. I'm going to start by giving you a little introduction of myself. If you don't know me, I've been working on PyO3 for about 4 years at this point. I wasn't the original creator of PyO3, but I guess these days I've long since been the most long-standing maintainer and kind of helping push PyO3 along for these last few years. I just wanted to say why I'm streaming really, which is just to say hello. Oh, great, perfect. Thank you, David. So I work for the team at Pydantic as my day job, which is I work 4 days a week there. If you don't know Pydantic, it's a Python library that's used for data validation, but it's got a whole bunch of use cases around basically data integrity, converting to and from JSON format. We're working on other things that I can't talk about quite yet, but we're going to announce quite soon. There's a link on my YouTube channel to Pydantic if you want to hear a little bit more about what we're building. But obviously the focus for today is on PyO3. Pydantic's implemented using PyO3. PyO3 is a package that is used to, is a Rust software that's used to implement Python software with a Rust core. You can also bind Python or use PyO3 to build Rust binaries which embed Python. Typically, I'm thinking about it the first way around though, which is Python software which has got Rust in the middle. And so on Fridays, I basically decided that there's enough that needs to happen on PyO3 that Fridays I put to trying to develop on PyO3. I've also got a young family, so having a little bit of flexibility on Fridays to kind of get on with PyO3 in time which suits me is pretty valuable. And so I guess to clarify on that point, David, so I joined Pydantic last summer. So I'd been working on PyO3 for a long time before I joined Pydantic, but once Pydantic decided that they were going to implement the core of the software in Rust, then I became a valuable member of the team, and so Samuel invited me to join. Where was I? I was talking about, oh yeah, so having Fridays to do a bit of streaming now is another way to kind of engage with the wider PyO3 community. I hope from these streams to both block out some time to work on some of the meatier issues that are going to be hopefully interesting for the community to see how we solve them. It's really something for people who are watching to engage as well and to offer solutions or ask questions as we go along. I'll try and explain what I'm doing. I don't really want to get into like the beginner level Rust stuff because I think it will make the development go too slow. But I will do my best to explain concepts and encourage people to kind of share and help describe if there are people in chat who need to ask questions. We should definitely, ask questions, and we'll try and cover as much of the material as we can so that people can follow along. Better that you ask questions and everyone follows what I'm doing than I just type here in silence. This is really meant to be an engagement with everybody out there. Cool. So with that, I think I might as well just jump straight into what we're going to look at first today, which is, let me actually bring up maybe a web browser as well. Let me see. This is my first time using OBS as well, so I've now got to figure out how to add another window without creating a big, horrendous mess of what I've already set up in the scene. Oh, can you see that all right? Can't seem to resize it, but never mind. We'll just go with this for now. So I've been working on a new API for PyO3, and we'll kind of get to the details of it in a little bit. But in particular, I had a review going on the other day. Is it this one? It is this one, which had a long comment thread. And in particular, we got to this point where we decided to make a change to what I've done in the review so far, which might need a little bit of think. And so that's what we're heading towards. It's PyO3 pull request 3705. Can I paste links into chat, actually? I don't know. It looks like that worked. So you can read on a little bit more if you want there, but really I'm going to jump across and try and show you the implementation and kind of why we got to the thread of that review rather than just reading out that thread on the screen. So let's take the browser away. I've moved the terminal. That looks better. Okay, so how's PyO3 built is probably a good place to start here. So we have in the PyO3 source code these procedural macros, which are used, I don't know if you've used PyO3 before, to implement basically the back end of how PyO3 works. So have we got like a nice sample? Oh, this was something I was playing around with the other day, which we don't really need the full detail of. But actually, this is great. This is perfect. So let's kind of start here like that. So, and in fact, we can make this even simpler by taking away this. So let's explain a little bit what we've got on screen here. So this is the kind of functionality that PyO3 offers you when you're writing Rust code to implement a Python module. These annotations here you may be familiar with as Rust macros. In particular, these are implemented as procedural macros. A procedural macro is basically you run some code which can input the code that's underneath and then outputs some extra code which you as a user never need to see, but the Rust compiler will use as input when building your final program. And PyO3, when you're building here a Python class, you can put some Rust content inside it. You can create Rust methods on that class, and you can create a Python module, which you then add that class to. So let's jump over to the terminal. Oh, that might be a bit small on the screen, is it? Can people read that terminal size okay? I think that's about the same font size as the editor. I'll assume that's a yes. Okay, so what we're going to do, let's go see what this code produces if I'll take this away, and this should now be without errors and we can compile it. So we have a tool in PyO3 called Maturin, which is used to, I'm just going to activate Python environment. Maturin's used as a CLI tool, which we can use to, as it says by the README, build and package crates with PyO3. And so the idea being that we can use Maturin as a CLI tool to basically compile this Python module, and then we can play around with it live and see what's going on. And then I'll show you from there what we're trying to change to get to PyO3's new API. So let's just do Maturin develop here. It goes away, it's going to compile our code. There's some warnings for unused imports, but that's fine. We've got the unused argument, but I want to leave this argument here because that's related to what we're going to be working on in a minute. And then just to show you what this code is doing, let's run Python, and we call this module PyO3 Scratch. It's one that when I'm just doing my everyday development on PyO3, I tend to have a Scratch project around so that I can just test out things quickly and then see what they feel like from the Python side as well. It's been a useful practice for me over the years. In general, I would probably add that, I'm sure that there's loads of things about my development practices which are not refined. So if anyone on chat has ideas on you see me doing something and you think I'm doing it a bit clumsily and there'd be a better way, then, give me a suggestion and I'm happy to hear it and try out new things. That's always welcome. So here we are. We can import PyO3 Scratch. Now we've got it. We have my class as a value straight away in the module. It claims that it's within the built-ins module. There's a long history there. I don't really want to cover it on this stream. One day that will be better, I'm sure. But what we did, we have a class method here. So if you have seen Python code, I guess the Python code might look a little bit like that's pretty much the equivalent of the Python code that we've written on the Rust side on the left. And so we can see we've got my class.sum class method. We can already call it. Oh, sorry, we didn't import it directly, so we need the module in front. And as we said, it does nothing. Let's just make it a tiny bit more interesting. So we could print out the class that we got. So we can recompile with Maturin again. And this time, if we call that class method, we see that it printed out what the class was, which is no huge surprise because we'd already printed it out previously directly. And so this is a good point to really step on to what's going on in the new PyO3 API. So we have this type, well, this is a reference to a Python type object. So in fact, if we wanted to have Python type annotations, it's probably something more like this. And we can even use, I think this is probably the correct annotation for it. I'd need to double check. That feels right to me. So we'll go with that for now. So it's a Python type object. And I mean, on the Python side, we're being a bit more specific. It has to be a subtype of self. Don't think we can do that on the PyO3 side. But we could take an additional argument to this class method. And so we could take any Python object as a reference to a PyAny like this. And the equivalent Python on the right would be arg any instead, imported from typing. So we could just print arg, I guess. We could do the same thing on the right-hand side. So let's run the Rust code again. Let's import the class straight through this time to save some typing. And this time it takes an argument. So if we don't pass it, you can see that PyO3 has noticed that we're missing an argument and has rejected it. And that's implemented inside PyO3's code, actually. We might look at that in a moment. But first, let's now pass an argument in so you can see it's printed the argument back out. That's fine. And then the thing that we're going to be working on, well, for PyO3 0.21, is that this reference to PyAny has turned out to be a little bit problematic. Basically, there's two lifetimes which are both stuck on this thing, but we can, because it's a reference, it only gets one lifetime to express it. It's a little bit complicated to get right into the full detail. The stream description, actually, I've put the number of the issue, which you can go read as much as you want on GitHub if you want the full context of it. But the basic kind of, if I was to try and describe it quickly, is that there are two things that you need to be worried about when you're dealing with this Python object here. And the first one is kind of like what you might have an intuition with from using Python directly, like Python argument or objects are reference counted. And so somehow in terms of Rust lifetimes, what that lifetime has got to imply on the reference is that you've got a valid reference to that Python object. Like that reference count is up by 1 for the lifetime of the reference here. And then at the end of that lifetime, whatever it is, then that reference count can go back down. And all of this is dealt with inside the PyO3 machinery at the moment. And we'll actually expand out this code in a minute. I'll show you what the procedural macro generates so that you can get a sense of what's going on. But the second lifetime, before we do that, is more to do with how Rust is interacting with Python. So the Python interpreter has the global interpreter lock. You might have heard about this. Basically, when you're interacting with Python objects, only one thread can really be doing Python-y things at a time. And that's set to change potentially as soon as Python 3.13. There's going to be a new or three-threaded Python, I think is the current terminology that the Python Steering Council are preferring to use for that. But ultimately, you will still need to be associated with a Python thread state when you're interacting with Python objects. So the constraint gets relaxed, but not entirely. From Rust, as far as you're concerned, there's still got to be some association between your Rust code and the Python interpreter at the moments that you're trying to do anything with Python objects. And so it was a long time ago, before I actually started working on PyO3, that people had the very great insight that we can use a lifetime on a reference like this to prove that we have that association with the global interpreter lock for that lifetime P. And so this allows us then to do things like we printed the Python object without even needing to care about it. We could do things like get its type and print that instead. Or we could even return that. And that returned value would be a Python type object. And it's still, again, got that same reference P, because that's the way that PyO3 has constructed things to work. Oops. People who are noticing Rust style might prefer to have no return there. Okay, so we could recompile this one more time just to show that that still hangs together. That's not where I wanted to go. I seem to have gone far too far into history. Let's just start again. Okay, so, and this is actually, the second one is the return value. So if we did tie like this, we can see that the thing that got returned from the class method was the type object of arg. Okay. And so let's first state what we're aiming to do. So we need to somehow break that overloading of this lifetime. This lifetime's got two uses for it: the lifetime of the reference itself, and the lifetime that the Rust code is associated with the global interpreter lock. We're going to expand this procedural macro in a second, and then you'll really get more of a sense of what that means. But what's the PyO3 API moving towards? Well, what I want you to be able to type is instead this, where we're introducing a new smart pointer. Which looks like this. And in fact, we can drop out these P's. Yeah, and I'm just going to see what happens here. So, and so what this bound smart pointer is doing is it's trying to solve that problem of the two lifetimes being conflated. So the bound smart pointer still has a lifetime, and that lifetime that it's carrying around is that lifetime of Rust code being associated with the global interpreter lock. So on this bound smart pointer, we can do things like call the APIs as we like. But it's also, because it's a smart pointer, it works like if you're familiar with RC or ARC from the Rust standard library, where you can clone those and a reference count goes up, and you can drop those and a reference count goes down. It's working in exactly the same way there. And so we've taken away that second lifetime. Instead, it really is just the type of the argument. And so we can try this. And then I might be pleasantly surprised here to see that this just works. No, this isn't working. So that's what I expected to see. So in the current API, we're still restricted with the current implementation that we have to still have PyType as the first argument in the class method. And that's what we want to fix. But first I'll show you that this compiles. Oh, it may not actually. It does. And that's because this, if we jump through, most of the methods on a bound smart pointer return bound objects. I haven't yet solved it for types, and that's part of what we're currently working on. So let's change this to be a getattr of the name of the, or is that going to, I think so, right? That should be the same thing, but just implemented from the Python side. And that will be, could fail, because that attribute may not exist. And also now we're going to be instead returning a bound smart pointer as well. Yeah, so that's working. And we should find, if we compile this code here, that we get the same result as we did before, if I've got my Python code hat on correctly. So yes, it's still given us the type of the integer as the return value from the function. But you can see that what we've had to change here is that now the return value of the function isn't a reference anymore. It is actually an owned bound smart pointer of any Python object, because we don't know what the type of it is when we just call getattr from Rust. And so here, no longer have we got this reference to some reference which is stashed away inside the PyO3 framework somewhere. We've actually taken it out. This is now, the reference is very much alive for the duration of user code. We could throw that away straight away if we wanted, or I mean, we could even clone it, couldn't we? So we could clone it. And then we could even print the ref count of this thing. And we should see the reference counts go up and down. What's going on here? Oh, I need to have needed to put the error handling on a question mark here so that I could convert this from being the result where it might fail to allowing the function to return early if it did fail. We know that it's not going to, so I could have put it with unwrap here, but I prefer to not make things panic. And then we can put the result back as an OK at the end. And so now let's just run this one more time. And we should find that we can see very concretely the reference counts going up and down. And because it's actually just the integer 1, the reference counts are actually kind of high already, aren't they? Up in the 90s. But we can see that very much when we... Oh, sorry, it's the type of class int that we've returned. So it's a type object, isn't it? There's 90 references around, and we made it up to 91 when we did the clone. I could probably even have put a print before, but this would have said 90 here. This would have gone to 91 because we did the clone. And then this would have gone back to 90 after we dropped the reference. So it's working like an arc. And maybe just for comparison, we're just going to rewind 1 second and put this back to be a reference again, just to show you the difference of what would happen. So we'll have to return instead like this. And what I expect to see is that when this drop is not very meaningful. Clippy's already telling you that dropping a reference kind of is meaningless. That's kind of a clue. Clone isn't helping. But what we'll actually see, I think, is this, that PyO3 will do it once, and then the reference count never goes up and down, and we don't get control over it. Yeah, exactly. So we've got 90, 90, 90. And so that's showing really what the difference is between this new API that we're moving towards and the original PyO3 API. And on inspection, it might look like this older API was better, but the problem is that by taking this ability for user code to actually control the reference counts to any meaningful degree, you end up in situations where memory use can be much higher than you want, because basically all references are having to go into the PyO3 framework. And I'll show you when we expand the proc macro code what that sort of means. But also it can work against you because there's the PyO3 framework code. There's a little bit of performance impact there as well. And so particularly when I've been looking at performance measurements for Pydantic, we found that we can get something like 20% speed ups by getting rid of this API. Another constraint with this particular API is that it happens to be, there's an assumption here about the way that threads are running, where basically a function runs top to bottom and the PyO3 functions are not interleaved. Like this function could call other Python code, which could go call other PyO3 functions, but eventually we'll come back here and finish, right? But it turns out there's a Python library called gevent, which implements coroutines on basically a single C thread. And this can actually break this assumption in ways that wouldn't have originally been obvious. So there's a reason also, there's an issue on it on the PyO3 tracker, but basically this API just cannot work with gevent. And so between the performance advantages, but also the fact that there is a problem with this API in the context of gevent, which is used sometimes for web servers, then there's good reasons to move away from it. Okay, so let's go back to the simpler code. And I might actually just take this and copy and paste it and thin this stuff down for now. And let's now run, let's look what the output of this procedural macro is before we try and see where we're trying to get to. So let's just drop all of this that we don't need. That's good enough. Great. So we're just feeding this argument into the class method. We want to change it as a reminder to look like this, but that won't compile, not because of the name conflict, but because this argument doesn't work yet, and we need to implement that in the procedural macro. Now, to look at what's going on in procedural macros, my favorite tool is this very helpful binary called cargo expand. I don't know if you've ever used this, but basically you can run it on some Rust code and it will evaluate all the macros basically, and then spit out the new source code once all of the macros have been expanded. So this is going to get quite sizable. I should warn you, it's not going to just expand these because the Rust standard library also adds extra stuff at the top. Let's take a look. So we'll run cargo expand. We'll expand the library and then we'll choose where we want to expand it. Let's put it into a file that we'll call libexpanded.rs. Okay, so that's finished. So we can open up this file. Let's put it on the right first. I did warn you. So let's try and distill what's going on here just a little bit. And then we can start picking apart what the actual implementation of what we're going to be changing is. So we've got here this, first off, Rust has added the standard import of the prelude. So that's things like the into and from traits, or toString, result, option, all go in the prelude. Stud is always pulled in as a namespace straight in. Then we've got our original source code. Maybe we'll try and indent left and right so that we can line it up for readers. You can see here, line 11, that one was, we had the class. And then what's happened is you can see that the PyClass macro annotation is gone, as I promised. And instead, it's been replaced by all of this stuff, which has come underneath. This is the PyClass implementation, and we can scan it very quickly. I guess let's expand over a bit. I don't really want to go into vast detail because there's a lot of things going on here, but really what's happened is that PyO3 has taken this code, these 3 tokens, struct, my class, with no contents in it, and from that it's learned, well, first off, that there's no fields that we're interacting with. It's a struct, not an enum, because PyO3 can also deal with enums, but it does them differently. And then it's gone and implemented basically a bunch of traits, which are useful in the machinery of the rest of the PyO3 code. And these are kind of all implementation details. There's a PyO3 impl module here, which has a lot of internal stuff, really, that the proc macros need to access. So you might see PyO3 impl all over the place in this code. And really, those you can access. They're all doc hidden, but you really shouldn't be, because anyone, like the goal of that impl module is that it's just there because procedural macros need to be able to access it, and it's not really for user code to access. And so, yeah, these traits just basically set up the stuff which would tell PyO3 how to create this my class type that we see in the Python side. So we can shrink that. Next we see, again, first off, well, the comments got stripped, but otherwise here is the implementation that we wrote of some class method. And we can see that, again, the class method annotation's gone, but so is the PyMethods annotation. Oops, sorry, seeing a comment in chat. Just want to touch bigger font size. Yep, sure thing. It's really helpful to have as feedback. Wrong way. How's that? I can do the same on the terminal. So I guess we might want to rearrange like this. Cool. Let's proceed like that. Hopefully that's a bit more legible. Let me know if it needs to change again. Thanks for noting. So yeah, we've got the class method here. We've taken away this class method annotation, and instead the same tricks happened again. Py3's omitted a bunch of stuff underneath. And actually, just to note, you might be wondering why it's written like this with a constant. The reason is that then we can start doing things like imports and have them not conflict with anything else which you wrote elsewhere in the code. So it's kind of like giving us a private block, if you like, to implement what we need. And so here is where we're going to start looking a bit more. We've got the PyMethods, and so we implement this trait PyMethods, which is telling Py3 how we'll load those Python methods, and there's some definitions of them. If you've ever looked at the Python C API, then you might have seen some of these FFI definitions before. Let's see. I'm looking to try and pick it out. It's actually not super easy to see just from the proc macro output. Maybe I'll switch over to a web browser for a second. Again. So we're heading towards I think this is probably what we want. Yeah, so in this is documentation for just the Python C API. So if you're not familiar with it, this is when you're building any native extension. So, I mean, we've got the PyO3 ones that we're talking about here, but also if you're using C or C++, maybe you've used tools like Cython or PyBind 11. All of these are interacting using the Python C API, which is how other native code can basically talk to the Python interpreter to create all of these Python objects. And in particular here for the PyMethods, we're going to create these PyMethodDef structures, which tell the Python API or the Python interpreter what these methods look like. And so it's things like the name of the method, the pointer to the code, which it contains a method. So that's literally a function pointer to the Rust code. We can go look back at that again in a second. Flags, and so the flags can include things like whether it's a static method or a class method. Here you go, some of the flags. So for example, meth class we'll be looking for because we wrote a class method. There's also different calling conventions saying whether it takes arguments by keyword or as a dictionary. I don't really want to get into the detail of all of these right now, but you can also pass a doc string to these Python methods. So let's jump back to the code that we were just looking at. So here's kind of where we're heading for. You can see in this bit that we've got our methods, which we've just got one of, and PyO3's wrapped these up into helper structures because we don't want to have to repeat basically verbatim C or C compatible code straight into like the proc macro output. Instead, like I said, we use this impl module to kind of get around some of the more complex things and make it reusable. We're probably going to be looking at that impl module again in a bit. And so here, I mean, it's a class method. We've said that. It doesn't take any other arguments. So we've created a no-args PyMethod_def. We've given it a name. This is actually the signature that we get, but there's no documentation. So if we go back to Python, we can actually see this. If we just look at the help, we don't get any docs because we didn't write any, but what we can see, we haven't recompiled this yet, but it's just telling us the name of the function, basically. We can, I think this will work. If we import inspect, we can do inspect.signature. If it doesn't, then it's probably a bug to fix another time. Yeah, okay. It's not telling us that it's a class method, which I was sort of hoping to see. But and this is old code from before we recompiled, so we're still seeing that there was one argument there. But the point is that this documentation here is how inspect learns what the signature will be for the native code. And then our function pointer, so we actually define this right here. We've created an extern C function. We just call them all trampoline at the moment. Maybe there's a better way to come up with naming all these things, but it calls through into the PyO3 impl module with an actual function pointer to do some more interesting stuff. And so this stuff I don't want to read right now, but it's basically to do with the fact that we can panic in Rust, and Python, the C interpreter, obviously doesn't want us to panic. Like, that's not a concept as far as the Python interpreter is concerned. So this trampoline stuff is really just concerned with catching those and translating them into Python exceptions or dealing with them in other ways. And so that's kind of reusable across all functions. And then the stuff that's unique for this class method is in a separate symbol that we've implemented down below. And so the procedural macros also expanded this one. This is the PyModule stuff, comes later, we can see. And so what's this function doing? It gets PyO3 Python, which is, we could even have handwritten this out. It's you can get this from Python methods just by doing this. And that's just a marker to say that we have the global interpreter lock, the association of Rust to Python code for this duration P. So it's just a helpful type which can be used in various contexts. I don't want to cover that right now, but there's lots of docs on the PyO3 API about it. It's useful for this internal stuff. If we search, we can see that PyO3's internal code is passing this around to prove that we have it so that it can do stuff a bit safer than it would otherwise, needing to make assumptions, basically. And then it's receiving also one argument, which is it's called SLF here. Kind of, it could be self, but it can't be self with a keyword. But really, actually, because this is a class method, this is confusingly, this is what's going to eventually be called class. And so somehow we need to get that from being a pointer to a Python object into this PyType. And that's kind of what's going on down here. We'll look at that in a bit more detail in a sec. But then finally, the last bit of this function signature is it returns. So it returns a PyResult, which is a user-facing type. We've looked at that before. That's just carrying a Python exception as the error. And then the success value is just the Python object for the result. So in this case, it's going to be none because we don't actually return anything back out. But when we were returning things from the function before, then those would have been the Python objects that we were returning instead. Okay, 1 sec, I'm just going to take some water. Oh, actually still coffee. And so this code here, we have, first off, turning the result into a pointer. We've got function is, this is a binding that I think we used because we had some kind of conflict. If I recall, there's an issue somewhere which describes it. But basically, we take my class, some class method, which is this. This is literally renaming that function to just be called function. So we could just simplify this code a little bit. I guess it would be the same thing. We could do that. There's some special case where that was helpful, but we don't need that right now. And so we're calling this function. We need to pass the PyType. And how do we get that? That's going to be this block of code then, which is that argument. And so what we see is we see that we use into to get there, potentially, because we allow a few different types. You could also have this type, which is a PySmart pointer, but it's not got a lifetime. So it's very similar to the bound one that we looked at earlier, but it doesn't have a lifetime, so you can't freely call Python APIs with it. This is useful when you need to hold a reference to a Python object for longer than you want to be interacting with the Python interpreter. So maybe you can save it across PyO3 function calls or other things like that. I won't really talk about that right now, but it's one of the types that we can allow through the into conversion. And when we call this API from type pointer, which is unsafe, and at the moment we don't need to mark that explicitly there because the whole function's unsafe, which is unfortunately just kind of the nature of a lot of this PyO3 proc macro code. I mean, it's taking a raw pointer, and doing anything with that raw pointer is necessarily unsafe because it carries no proof that it is actually a valid pointer to dereference. And so the correct thing to do is to mark this function as unsafe, and then we just have to be aware of the assumptions we're working with when we're handling this raw pointer. What's the cost of converting from PyO3 to reference to PyO3? How does it work under the hood? Great question. So with all of these 3 types that we were looking at, so the choices we've got the old one, reference to PyO3, and this is literally the same layout as what's a nice way to write this? So these 2 things have exactly the same layout. So the reference to PyO3, a Rust reference, is kind of like a pointer. And so the current PyO3 API treats these these can be thought of as equivalent. And so, but as we say, this is kind of going away. We've got PyO3, and we've got bound PyO3, which will be the 2 things that will be in the new API. So while PyO3 already exists, and these are the new things that we'll be working with. Let's put them the same way around. And again, actually, these are smart pointers, so they're pointer types. So they actually contain the same thing again. So all of these types are just the same. They contain 1 pointer internally. And we don't let you get that pointer. Well, actually, sorry, that's a complete fib. We do. So you can call .asPointer on any of these functions, on any of these types. to get access to that raw FFI pointer. That's a backdoor that you only should use if you need to start doing the raw FFI stuff. Which generally the goal of PyO3 is that we want to provide safe ways for you to do all of the common interactions without needing to go to FFI yourself. But sometimes there's edge cases that you might find it useful to interact with the objects directly. But so all of these types, more going back to your original question of cost of converting, are exactly a pointer in layout. And so the cost of converting from PyPyAny to referenced PyAny is basically nothing, because if you have this code, something like this, so you have the Python marker, and you have, I'm sorry, this is pseudocode that Rust Analyzer is absolutely hating. But if you have these two things, then you could get to the reference form in the current API by just calling this as ref. And that's literally just reinterpreting the pointer as a different thing. And that's safe to do. This owns the reference. And so this is borrowing from that owned reference. And so the lifetime here is basically for as long as this borrow lives. It's not quite the same Py. It's a restricted one. In the new API, it's going to work much the same. So you'll have, you could have the same thing for the first two. And then the only difference is that you could end up with this type where the lifetime of the inside the bound is exactly the Py. And the only difference isn't calling, instead of as ref, we've killed the method bind. And so this is basically something that will compile away to zero cost in either case. This is taking a borrow more, again, because we're making this new API actually express like Rust ownership correctly, you can see that this is a reference, but there's another form we could have where we don't take a reference, where we're instead going to do into bound. And so in this case, X is no longer alive, X2's borrow will have to end, and X3 now owns that Python reference. And again, this layout is just the same as a pointer, this layout is just the same as a pointer, so this, as far as actual compiled code goes, it's a no-op. But in the Rust type system, we've transformed the type by adding an association to the Python interpreter in there with the lifetime. And so same here, this is a no-op in the current API because it's the same actual layout in memory, but we've just associated it in the type system. Cool, so that was a bit of a jump. Let's just move that out. We'll put that down below somewhere on this scratchpad. Great. And let's get back to here. So we call this method from type pointer, which is going from the FFI pointer into the PyType object. And so actually this method itself, we can go look it up. Here. From type pointer is an unsafe function because it's taking a pointer, so we can't promise that that pointer is actually valid. We can see these are the safety environments that we're asking for. The pointer must be non-null, so we're making that assumption that Python is behaving correctly and passing us a non-null pointer when we're calling this. That assumption we don't actually check for non-null in this code, so we're trusting Python's actually given the right thing further up. And that's supposed to be a guarantee of the Python interpreter, so we're going to rely on that assumption in PyO3 for performance reasons. We could check it if we really wanted to be safer. But I think it's correct to rely on the Python interpreter being built correctly, because if that were not the case, then that would probably be treated as a bug in the interpreter, I think. And then the second constraint is that the pointer must be valid for the entirety of the lifetime for which the reference is used. And that's because if we add lifetime annotations to this code to make it more explicit. What's going on is that we've created that reference with lifetime pi. And so we've just made a claim that from the sake of calling code, that this reference is alive for that lifetime. And where is that lifetime coming from? Let's go look back at the proc macro code. And yes, we're going to need to jump into these trampolines actually. So we see that the original pointer that we're giving to the C interpreter, to the Python interpreter as the external C symbol, just takes 2 arguments, which is what the Python interpreter expects. Self, in this case, is going to be that same thing that eventually becomes the Python type object. So as a reminder again, this is eventually called class, but self is just what it's called in the convention in the Python interpreter at this point. And then args, this is going to be null in this case. And we know that because this is a no args. And so we're never really going to do anything with args in a no args trampoline. We'll go look at that now, because that's going to tell us a bit more about this thing, pi, which has come into being for our class method. So again, let's look at that. No args, we've forwarded the 2 pointers that we received from the interpreter, and we've told the trampoline that this is the code we're calling, which is this one down here. And the trampoline, we'll go look at that in a sec, gives us the Python object with the lifetime that is eventually going to be the thing that we're calling for. And so the promise that we've had to make with regards to lifetimes at the moment is that this sum class method, the reference that gets created by this stuff, has this lifetime pi, which needs to outlive whatever sum class method does, which can include returning a value with that same lifetime pi. So basically what we've got to promise is that this lifetime pi lasts for all of this code, which it does because of the way we've constructed things. If you pass in a lifetime like this to a function, then necessarily that lifetime lives longer than the whole function body. That's just basically something that we can guarantee about Rust lifetimes. And so in the way that the current API is formulated, going back to the constraints that we had from type pointer, we know it's non-null. We've talked about how that's guaranteed by the interpreter, and it must be valid for the entirety of the lifetime for the reference being used. And we've just shown that by construction of how we put the API together, I understand this to be true. Great. And so now, as I promised, we need to go look into the no-args trampoline just to see a little bit about what's going on there. So let's jump over. This is inside PyO3's impl modules. So these are publicly visible symbols, but they're all doc hidden. So you shouldn't try to call these. It's not. It's in the conventions of how Rust semver compatibility works. It's not semver breaking for us to change these in a patch release. We don't intend to generally, because we only make modifications to this stuff when we need to. But the point being that if you depended on anything in the impl module, then we might break your code at any time, and that's kind of allowed. This stuff we wouldn't actually want to be part of the PyO3 public API. It just exists so that the macros can do things. Okay, so what we've got here is, here's the no-args trampoline. It's right here at the top. So we passed it the 2 pointers over from the macro code, and then finally some function pointer, which takes 2 arguments. So it'll take the Python token, and it will take well, in this case, it's going to be class. It's going to be self is going to get forwarded through. We can see that here. And we actually, the args pointer, I promised you it should be null, and actually we've got a debug assertion here that it is null. I'd forgotten that that was here. So in release mode, we don't bother checking. If you're running your unit tests with a debug build of your Python module, then should for some reason the Python interpreter not be giving you this as null, it would crash with a panic. And so I don't think I've ever seen this assertion trip, but it's good to be there in practice. Okay, and so we have this trampoline helper, which I was talking about, that basically is dealing with panics. And also, this is really getting to the meat of the API difference of what we've got going on in the new versus old PyO3 API as well. We create this structure called internally in Python the guild pool. It's not a pool of global interpreter locks, so the name might be a touch misleading. But what that is, that's an internal data structure which deals with thread local storage and keeps alive all of those Python references that PyO3 is interacting with so that they have the lifetime pi. So if we just rewind back to when we wrote this code here, where we ran a getattr and it produced a new pi any with a reference to lifetime p, that's still the same lifetime pi that we're having over in the macro code. And where does that lifetime start? Well, it starts here when we create this pool and then borrow it in particular to get the Python. That is where we're creating Python pi. And this lifetime ends when we get rid of the pool, which I guess it's going to be, morally, it's about here, I think. Is probably a good way of doing it. We want to do it explicitly. So the pi lifetime ends here, as far as that promise goes. And so all of the references are okay to put into this dual pool, and then everything that's running down into the proc macro code, eventually coming out into your class method, can hold this Python reference for the lifetime p, because we know that it's going to last the whole time. But as discussed, putting all these references into the pool with the older API has performance and also compatibility concerns with gevent. So this is to go. But either way, we'll still be able to prove that we have the association of Rust code to the global interpreter lock. So eventually this will be rewritten to not create a dual pool, but we'll still create a Python token that will have this lifetime pi. This bit's going to look different, but will produce the same type. This goes. This will have some like create Python trick here. I think there might be a pull request actually where that change is in draft. I can't remember, but it's not too hard to solve that bit. Okay, so we're just showing that and how that works. Let's reset these changes before we create confusion for ourselves later. Great, yep, that's got no edits anymore. So where were we going with this? Oh yeah, so that I was just showing where the lifetime came from. And that's kind of showing you how everything hangs together. So going on to the code that we're now trying to implement after, I guess, a fairly sizable intro to how PyO3's API will be changing, we want to get this one to compile instead. And where we're taking bound. Now, we could take bound by value. That would be equivalent to taking ownership of that pointer. But at the moment, we don't have ownership of that pointer in a Python reference sense. Python's just like telling us where the Python object lives. We could. But this is probably more akin to what we actually want. We're going to borrow that reference that we got passed for some duration, which we don't really care about this duration anymore, because all it is that it's alive as a reference for while we're working with things. This Python lifetime is helpful, as discussed. And so this is what we want to compile. And if we run this at the moment, what we'll get is, because we've got the into over here, it says that the trait from PyType is not implemented for bound PyType. And actually, I could solve this fairly quickly, maybe, by defining that conversion, but that's not what I want to do. I want to get rid of, in this code, the fact that we even ever call from type pointer and create, at this point, we're creating this thing that's in the old API design, right? We're creating a reference to a Python type. And so we want to design maybe something new here, which takes I guess, let's think about this. So we probably, or the simplest thing we could do is we could just create this type instead, I guess, is where we want to be going. And so, yeah, that's what we wanted. And then we can allow the into to work. So let's think about this. This is a reference to a smart pointer. And let's go look at the definition of so over on the left, we have the structure bound. And as I promised you, it's actually a bit convoluted, its implementation, but it has that Python token inside it. This is a zero size type. It's repr transparent, which means that semantic, or as far as the compiled layout goes, it's got an equivalent layout in memory as its only field that has an actual size, and that's this field. So we can jump down again. This is again transparent, and it's a wrapper around non-null FFI PyObject. And I think even if you go to the Rust standard library, it's repr transparent, and it's actually const t. I guess that's interesting. I don't know. I assume that it's. I normally think of non-null as being a wraparound. Yes, mute t. So that's interesting to see that non-nulls internals it has const t. I assume that there's some folks on the Rust language or library team who can tell us a bit more about why. But as far as I go, I think of non-null as being equivalent to this, but where we've made that assertion that there really is no null, so we don't have to do that check anywhere else that we're dealing with that thing. So going down that rabbit hole, what I'm trying to get to is that I think it's valid for us to take this reference, for example, reference to the Python object. And so let's just write this here. And I know that we're editing the procedural macros expanded output at the moment. So this isn't actually changing any implementation at the moment. I'm just kind of drafting and showing you where we might be heading. So we want to get to, we'll call it next. So we can do a reference to the pointer. And then it should follow, because it's okay to transmute one of these to a, well, it's not okay to transmute one directly to a bound unless we also know that we're taking ownership of the pointer, the Python reference. And we're not taking ownership of the Python reference here, which is why we're introducing a Rust reference to the pointer. Then I think we should find that it's okay to do a transmute like this. And I should comment here. Transmute is pretty mean. It's like a last resort when you've got no other way of converting one type to another. And oh, sorry, why is bound p better than p type? Okay. Yeah, I'm going to say Amaruddin. I'm sorry if I've got that name wrong. Yeah, so there's an issue linked in the stream description, actually. Not linked, sorry. It's just an issue number, because I forgot to get YouTube verification for putting links in the description in time. Didn't know that was a thing. It will talk about why we're migrating away from that API. As far as that question you asked earlier of the conversion, it's not got any performance implications, but it's got performance implications in other places. So bound is both faster, but also moves the ownership of the references more directly into user code. This takes away overheads from PyO3's framework. It makes memory performance better, as in you can use less memory this way because you get more direct control over when the Python objects are being freed. And it's got a conflict with G-event in the old API, which is quite seriously problematic. If you try and use PyO3 with G-event, you're going to run into trouble. And so the new bound API basically gets rid of that problem by taking away the PyO3 framework from the picture. So yeah, there's good reasons to make that move. And so we're wanting to get to this point. Okay. And so talking, a bit more about transmute. Basically, it's okay to transmute this type into bound, but bound also conveys ownership. So if this was an owned pointer, we could do this transmute because the layouts are the same. And we check that because there's repr transparent on the whole things all the way down till we get to a pointer. Where did it go? Yeah, it's repr transparent all the way down from bound into Py to a pointer. So we know that the layout is the same, and we can do that transmute. And then but we don't want to take ownership of the pointer. So that's why I wanted to play with this reference idea of transmuting a reference to a pointer into a reference to bound, because that way we're never claiming to have ownership of the Python reference. So I think that this is the right way to go in this API. And then after that, we actually wanted that. So this in the new API, we can do one more time. We can probably do an unchecked downcast. So downcast exists in the current PyO3 API. We're keeping that in the new bound API as well. It's the way that we can convert from one type to another. So we could do it like this and then check the error. So this downcast function basically checks whether the Python object that's currently of type any is actually a Python type object. If it is, then this will succeed. If it fails, then we'll bail out. But I think in this context, we're probably okay to assume that the Python interpreter, again, not only is this self object non-null or self pointer non-null, but it actually points to a Python type object. So we can make that assumption. And then that is potentially more what we want, like that then. But rather than putting it into the proc macro code, maybe we'll go make a helper for this at the moment. So let's first go back to the PyO3 repository on the left. Okay, so we're on main. Let's call this branch. We'll call it class method. Why not? And so we want to make a modification to PyO3's proc macro code to achieve this transformation. Let's start by putting that into maybe an impl module somewhere. So we've got in the PyO3, I'm going to close this right-hand side now, I think. We can always come back to that if we want, just so we have a bit more space. So we want, in this impl module, we have lots of different helpers for different things. This is probably going to go in Py methods for the moment, and we might as well document this. So so let's create this function. I can't think of a good name for it right now, but what it will take it might as well take pi, because that, again, at least guarantees that assertion. And we don't need to do this. So what we've said is that layout equivalent wise, these are the same. Bound is layout equivalent to a FF5 pointer. And then, so for the moment, I'm just going to put that stdmem transmute in here. So maybe there wasn't much. Oh, we need to import that. Yeah. Oh, yeah. And so we're having problems here because there's 2 lifetimes which have come into play, which is not a huge surprise. So first off, we've got the pi lifetime, which is the time that we can safely interact with Python objects. And then we've got this reference to the pointer, which we're deliberately constraining here to be the time that we had this pointer around. This is going to be an unsafe function. And what are the safety invariants that we're asking for here? So first off, we're making the assumption that it's non-null. And also, we're making the assumption that this Python object continues to exist. So pointer is, how do we express this? Owns a Python reference for at least the lifetime. Okay. I think that's the right way to express it. And what we're asking for, rereading those comments, is actually that I don't like this name very much. If anyone's got any suggestions for a better name for this thing, I'll take it. But implementation wise, what we're saying is that we know that we can safely call Python APIs, which is what we're needing in principle to create this bound type of tool. And we also are saying that we have a pointer, which is non-null, and we are not directly moving that pointer into our bound ownership, but instead we're treating that pointer as a bound that's referred to somewhere else, which is fine because a bound, as we've talked about before, is layout equivalent to one of these pointers. And the constraint is that this lifetime A, it has to be meaningful. The Python object actually has to exist for that duration A. And so that's what the second bullet's trying to get to and describe. And so with those assumptions in place, then it's okay to go into PyO3's safe API paradigm for at least that long. And I think rather than a transmute, we can probably get away with doing a pointer cast instead, which would be, can we? No, maybe not a pointer cast because this is a reference to a pointer. But what we can do is we can yeah, so we can cast, we can avoid the transmute by, it's a reference to a pointer. So a Rust reference can be cast to a raw pointer like that, or Copilot's being helpful for that piece. So this is okay. It's basically, we've gone from a Rust reference that's got a nice lifetime to a raw pointer instead. This is not a mutable reference, so we're going to a const pointer. And then now that thing, we can cast it. So pointer cast, takes some pointer. So at the moment, this is the pointer type. It's a pointer to mutf by object. We can cast it to bound by any, and then we can change it back from a pointer to a reference by whacking this on the front to basically dereference it. There might be a... We can actually... This is probably preferred, isn't it? As ref unchecked. Oh, that's what we want. Sorry, scanning around to get to that. Does that exist? I haven't used this method before, but it feels probably nicer than dereferencing. Missing an angle bracket. Okay, no. But I suppose what we could do... yeah, okay, fine. Sorry. the documentation is talking about this. So I was trying to avoid adding this, but actually that's what the documentation is recommending, and it's what I've always done in the past. So if you know that the pointer can never be null and want to dereference the point, then you want to get to reference to t. So we want to get to reference to bound, and we have a pointer that's a const pointer to bound. Then the documentation is suggesting that you dereference the pointer and then immediately add a reference back on. So that is avoiding the transmute. I should comment here that we're fiddling around with pointers, and this is unsafe. And this isn't really what most Rust software will want to be doing in a safe paradigm. Like, this is a consequence of the fact that we're coming from the world of C, with Python objects described as pointers, and we're somehow having to transform them into safe Rust types. And so we've done this reinterpreting of the pointer, and if we've got this all correct, which I believe it to be, we can run some tests in a minute and see what happens. Then this will work fine. But really, if you're dealing with safe Rust code, you should think about using references and not converting them into pointers to reinterpret things. That's really a bit drastic. You should be using Rust structures properly. And even more, we had transmute written here for a minute, and transmute is kind of like the next level of evil on top of all this pointer manipulation. It's for when you can't get the pointer manipulation to even prove what you want. So this works. It's probably good enough. It displays our intent. It's putting the right constraints onto our output type, most importantly. And so now that we've written this function, the next thing that we're going to have to do is carry on and actually put this into the procedural macro code. So we're going to have to search for that, aren't we? We call the function that's currently being used is this one, from type pointer. This looks like the right place. This might look a little familiar. So we should probably talk a little bit about procedural macros before we go further. Give me one moment. So how to... question on font. So the font is, I think it's JetBrains Mono. Yes, JetBrains Mono. I tried the recent GitHub fonts. I didn't actually like them very much. I found I'm not a huge fan of the JetBrains IDEs. Like, they're great and they're powerful, but I prefer something a bit simpler. And so that's why I've been a VS Code user for a long time. But JetBrains make an absolutely brilliant font. I'll just repeat that to clarify. There are many use cases where the JetBrains IDEs are fantastic. It's just not my preferred choice at all. And then another question from Ozio before we go on to the procedural macros. Looking at the definition of bound, I see it's taking Python Py, but you're not parsing it, right? You mean in the method that we've just implemented here? Yes. So maybe a better thing to do, that's a great suggestion, is rather than just doing this manipulation here, let's go make a create private API to deal with this a bit more properly. Okay, yeah. I might add documentation later, but let's just go a bit faster. Maybe this is helping us get to the right place as well. So from reference to pointer, it's not going to be fallible, and it's going to take Python, and it's going to take the pointer as a reference like we just built. And now what we could do is we could actually use Python. This probably is better. So bound was a Python type, or it was a tuple type, with the first type being the Python, and the second type being manually drop PyT. And so I didn't actually look at manually drop, but it's repo transparent as well. So what we want to do now is rather than cast to bound, we can cast to the inner type, like this. No, is that a problem? Oh, that's not going to work, is it? Because this reference isn't what we want here. We want the reference to be out there. So we can't do that. So we're not going to be able to pass Py any further. We are going to have to go backwards. And so I guess answering more directly your question, Ozio, Pi is a zero size type. So all it serves, zero size means that in compiled code, it actually doesn't exist. It's just like something in the Rust type system that's allowing us to promise that we have this ability to interact with Python. And so we, in this repo transparent type bound, this thing doesn't actually occupy any real space in compiled code, and we can cast pointers into things which, or pointers of things which look like this right-hand side, without ever needing to care about Python. But we do want to attach a Pi lifetime to the bound because we want it. So we can't actually feed Pi in, but we can ensure that that association is made on the lifetimes by taking it as an input. Actually, Pi is a type is a lifetime already on the thing. So by requiring the Pi as an input lifetime, then it guarantees that this thing that comes out is carrying that same information through for the Rust compiler. So even though we don't use this argument, it is helping us build a safe abstraction here. Oh, yeah. And this is probably better anyway than what we had before, only because if I jump back here, I'm just going to use this implementation here. And for the sake of performance, it's probably right to inline this thing. It's only a single tail call, and similarly, this is only a pointer cast, which has no real like performance impact because it's just reinterpreting a pointer. So by making those both inline, it's probably correct, and it will just mean that those compile away to absolutely nothing. Why is it saying it's not used? Oh, because this function is not publicly exposed. There we go. Oh, wrong way around. Okay, great. So we now have this function available to us, pointer to bound, from the impl crate that we can use in our proc macro code. So let's start talking about proc macros now. So where did we lost it again? Here we are. So what proc macros do is that they take some syntax or Rust code as text input, and they're allowed to produce new Rust code as text output. And they are a program that does that. And that's basically the whole definition of a proc macro. And so if we look back at what we had, we're trying to get this code to pass correctly. And so what's available to the proc macro? Well, it knows it's a class method because that's part of the annotation. It knows it's a function with that name. It gets the information about this lifetime, not actually in any meaningful sense of a data structure, but it knows that there is a lifetime called P attached to the function because that's literally the text that it sees. It knows that the first argument is called _CLS, and it knows the type of the first argument. Again, not in any kind of way that you can learn more about this type, but it just knows that there is a type that is named this because that's the text that is written there. And at the moment, PyO3 doesn't do anything with the function bodies, but it could analyze the contents of the function body and learn stuff from those as well. So as far as the proc macro is concerned, we need to get from that to, we looked at the expanded stuff before. We're going to emit code that looks more like this, quite a sizable piece of code to emit. And then I said that we obviously can't probe those types for any meaningful properties, but what we can do is we can use the Rust type system to enforce good behavior about the stuff that we actually emit. So we can splat out as much Rust source code as we want, but by using traits or things like that, we can actually have more advanced logic work. So the proc macro doesn't do that advanced logic, if you like, but it has to prepare things in a way that advanced logic can work. We'll probably, in this implementation, we're not going to need to go that much into the detail, but if we do, for example, other stuff, these Py methods you can implement things like add, for example, the Python method. That's not the right signature, is it? It'll take self and it'll take some other thing, which looks something like this. If you've written Python operators, you'll know that this is the implementation of plus. And the PyO3 procedural macros have to do some smarter stuff for these kinds of methods. And so if we ever need to do some development of that, we can learn about how that works, and we'll see some more advanced techniques. So let's go back over to our procedural macros. I've lost it. Here we are. And so this is the fragment of code that we saw before in the expanded macro output. First off, it could be a useless conversion from the Clippy lint. I didn't talk about this earlier. That's because we use into to give us the flexibility we want, but it's quite possible, as we see here, that the thing that we actually want in the user-facing code is just the thing that we produced already, or in the way that we're going to change the code, it's going to be a reference to bound. Before it was a reference to PyType. But there's no into conversion needed there. But if you wanted to take, for example, this one, which does compile already, using the PySmart pointer instead, then we need the into conversion to go from this to this. And this owns a Python reference. So that into conversion it's increasing a Python reference count somewhere, but it's not a huge cost. So it feels like it's appropriate for an into conversion. Okay, so let's go back. And so having written our new function, we can use that. It's going to be, what do we call it? It was in Py methods, and we called it pointer to bound. And it can take then these. So to build these procedural macros, we're emitting this code fragment, and it uses another macro to build these pieces of code called, it's a crate called quote. I'm not going to go look at the quote documentation here or anything. You can look that up in your own browser if you want to, but it's a macro that allows you to basically glue stuff together using these pound whatever fragments to basically stick in other pieces of code. So so that then you don't have to like literally type out the code you want, but you can build it up from other logic. And there's not too much going on here. We're just creating idents and we're giving them different spans to the other stuff that we're emitting. I don't want to talk about macro spans right now. That's probably a more advanced topic that we'll cover another time. Yeah. And so we've created just two identifiers, pi and self, and we saw those in the emitted code, right? That they were called, we've already modified this quite a bit, but they were called pi and self. Maybe I can, let's go back to this and regenerate it quickly. Here we are. Oh yeah, we've put quite a lot more code in now. But here's what we were looking at, where those two symbols, pi and self, we just saw over here, but we've just rewritten this. So now we're taking reference to self and we're going to use pointer to bound. So if we save this now, then we should be able to recompile and we'll see whether it all works. It looks like it has, which is exciting to see. So if we go back to our expanded code this time, so we've changed it now in our procedural macro output. We can see instead that we've got, we're calling our pointer to bound function, which we've been busy building, and it's going to produce, or it's going to use the into conversion to go from all the types that we care about, or from the bound, the reference to the bound now into the other types. And if we go back, let's see if we save this, it's not. Oh yeah, we've got a little bit more to do. This still doesn't compile. It's telling us, I don't know if you can read that super clearly. It's saying pi type from bound pi any. So we forgot to do a type conversion. And for the moment, I'm just going to add that downcast unchecked, which we talk about here. It might be that we should have put that into the impl module. So we want PyO3 types pi type. And for reasons with the procedural macro output, we kind of want to avoid importing other stuff. So we have PyO3 crate available, and we have stirred available, and we can refer to like the fully qualified paths of things all over the place. So the code looks quite verbose, but it hangs together. So now we're not checking that the actual type input was a type object. We're just making that assumption at the moment. That might, that's consistent with what we had before. Before, if we just dash for a second just to compare, then before we were just casting here in the proc macro code. So we were previously just assuming that the type was a Python type object anyway. And so as far as the new code is concerned, we're keeping that same promise. And maybe there's reasons to revisit that or check that in the future. Probably, again, I haven't verified this myself, but I think that the Python interpreter is probably guaranteeing that you're passing a type object there. So it's probably fine to keep that assumption here. So there we've got it, and we should be able to go back. And so now we're seeing that our original two types are failing. So the only piece that I guess is left is we probably want to put into conversions from this type into the other two types. Let's think about that. So the only reason I'm hesitating is this is the preferred API for the future of PyO3, right? This bound type, and this is the backwards compatible one. And I didn't really want to make it easy to go from the new API to the old API. I wanted that. So I say easy. We have a method on bound to do exactly that, which we call, as GLRef, which takes the bound as a reference and returns out that it's a bit mangled from traits, but basically this would allow us to do bound. Actually, we need to put a constraint like this. The pi lifetime appears here. It's probably more correct to call it A for some shortened lifetime, because we have to guarantee for the output reference. Oh gosh, sorry. Yeah, that it's only got one lifetime, and that lifetime has to encode both the lifetime that the reference is guaranteed to be alive, which is this reference to bound, and the lifetime that we can encode safely using Python APIs, which is this one in here. And so we have to kind of constrain these to both be the same. In reality, this is some longer lifetime pi, but because we only get one lifetime on the output, we have to lose that and force them to be equivalent. But the point being that I wanted it to be noisy when you go from the new bound types back to the older API, so that when you're reviewing code or looking at migrating from your one API to the other, you're very clear about you've introduced the conversion there. So you can do it. It's just a function call. But I didn't want it to be something that just happened behind the scenes too much. And so going for the fact that we've got this into conversion here, which I'm not entirely a fan of. I didn't want to have this into conversion. I think my thought on how we could solve this, maybe what we can do is we could create a new type which wraps the bound type, and that can implement the into conversions to all three. And that should solve the problem. And again, more or less, these things should all be quite straightforward to then have conversions for. So let's go ahead and add that. So I'm going to obstruct. We'll just wrap this with a new type. And what a new type is, for those who aren't familiar with this pattern in Rust, it's basically you take one type. In this case, we're taking bound, a reference to a bound pointer, and we're packaging it inside a new type, which we're renaming, with the advantage being that on this new type, we can implement all the traits we like, and we don't get affected by any of the traits that were available in the original thing. And so what do we need? We actually want here, we wanted the into conversions. So we can do impl, we'll implement those as from. Yep, so that looks good to me. We probably need to add a lifetime here again. And so this is what I mean. We can have the as GLRef conversion here now. And we can repeat that for the other two types. So the other one is the obvious one. And that's easy enough. And then the and in this one we can keep the two lifetimes unconstrained. And then the final one is for we wanted pi as an own type. And in that one, we don't care about any of the input lifetimes, because the output has no lifetimes as well. So we can just make those all anonymous like that. And so we have here a reference to a bound. We can clone it to create a new Python reference, and then we can unbind it, which you can see the documentation for there. And what that does is that takes the bound type. It's the inverse of into bound, which we saw when we were talking about it at the beginning. This is as far as like as far as compile, like it takes that Python out. We can actually look at the implementation for it. So it's done through a transformation rather than getting the inner. That should probably have been. Maybe there's a better implementation for that. Maybe it should be self.1 into inner. Can you? I'm just going to look up on manually drop. Can you get a value out of it? Yeah. Extracts a value. Yeah, fab. So actually, probably what this implementation should have been is this. And here's why we had to do that. Yeah, so we couldn't move out because of drop. So that's why I had to construct it like that before, where I basically converted into a raw pointer and back. But again, all of these are basically zero cost as far as actual runtime goes, because it's just, they all have the layout of a pointer. It's just transforming things in the Rust type system. So unbind is just taking bound PyT and turning it into just this PyT thing. And so we can have that one here, but because that takes ownership, there's no reference here anymore. We first had to clone it. And those should be good. And now, we need to import this thing as well. Now if we go back to our sample, it still doesn't compile, and that's only because in our procedural macro, we're now just going to wrap this thing like this. And that's probably the full problem solved, I think. So now we have that written. We could go back. Let's go back to our Scratch module. We should be able to run mature and develop now. It all compiles. And we should be able to call all those methods. That's 2, that's 3. Yep, they all worked. I mean, they're all doing nothing. But the important thing is that they all compiled. So let's actually make them all do something. We could, let's just print the name of all of them in the same way. And we should find, again, that the part of the point of the, is it called this? No. I thought that this method existed. Yeah, okay, of course. We haven't implemented that yet. That's part of what we're still working on in the new API. So we're not going to be able to do that. We could do it like this instead, which should work the same. We're going to need to start dealing with results here, aren't we? We're going to need to start putting some OKs on as well. Great. So in the new PyO3 API, once we've fully implemented everything, it should be that this code, class.name, would work exactly identically in the upcoming API. And so that's what would pretty much the pull request that I mentioned right at the beginning of this stream. was looking at. I was implementing these methods, but I ran into this interaction about class methods that had some implications, and we wanted to fix those at the same time. And so that's how we went down this whole rabbit hole, really. And then we can implement for the final case as well. So for the final case, we can't directly interact with this object, as we've mentioned before, because we don't have any proof that the Python interpreter is associated with us, but we can solve that. We can take it as a separate proof, and then if we use bind, we're going to go from Py type. This is going to create our bound again in the same way. So then we can do the same .getAtter as we're doing here. It's exactly the same type at that point once we've done the bind. And so this should compile in the same way again. And we should see the same result. Kind of just, I'm doing this just to demonstrate that apart from the fact that we haven't implemented .name yet, it should work exactly the same way with the new and old APIs for this point. Yeah, oops. Yeah, so the original 2 and 3. And that's because probably really .name is using qual name under the hood, I suspect. There's probably a tiny wrinkle from history that we might want to clean up sometime. Nope, there must be something more to it. I'm sure if we dig around into exactly what's going on, we could maybe learn that. It's probably something like .name is getting the full name, which includes the module and the type's name, and then qual name and name aren't quite that, are they? So maybe we just need to get this API implemented for the full equivalence. It will work the same. That wasn't quite as positive as I wanted it to be. Right. Just to wrap up this implementation, the last thing that we're going to really want to do is add some tests. And so let's see if I can find where we use class method in some tests at the moment. Let's see, I'm just going to try and find a nice location in code. This is probably a fine place to put it. So in the PyO3 module, we have a subdirectory pytests, which is basically a Python package which we go and build, and it then runs pytest. Something's wrong. That's interesting. We got a I suspect that there's something else. What was the code we were just modifying? We were just modifying in these tests. Yeah, okay. So we were changing a new, which probably has some extra complications with it. Okay. So this is then like a constructor as well as a class method. There's probably something more complex going on there. Because it's going to be going through a different proc macro code path. So I'm trying to think how the best way to debug this would be. We might want to, let's put this back into our Scratch for the moment. And let's just put a new class method. So this will be the way to build the thing. In Python semantics, the equivalent is going to be something like oh, well, no, it would be more like this. Oh, no, sorry. It's more like this, of course. So Python has a new operator, which would return something. I don't know what, can't think off the top of my head what the implementation would be, but it's slightly different to like any other class method is my point. And somehow, well, this is going through a different proc macro code path. And that's why it's not compiling. So I guess we need to expand it and see what we can learn to double check what's going on there. Where are we looking? So we are looking at the one called new. Here we are. And this is what must be being called. So, and in that case, it looks like actually it's already coming through from Python as a PyType object. So I'd written this downcast unchecked where I was doing it after, and before, if you remember, the code had the cast here, and interestingly, that seems to be preferred. So actually, I think I quite liked the downcast unchecked. And again, pointer casts are no ops. So I might put this cast back here. So this cast is then in that case going from a PyType object back up to a PyAny, and then this is going back down. But these should both compile away as no ops. So it's more just getting the Rust type machinery right. So let's go back to where we put that in. Oh, yeah, it was in here, wasn't it? Suggestions for names on this function are still very welcome, by the way, if anyone has one. Right, so now, having done that, I think everything will start coming together. No, it still doesn't look right. Ooh. Oh, that's fine. That's because a new needs... that's basically completely unrelated to the original problem. That's because if it's a new, we need to return an actual content. Oops. Here we are. That should now compile. Great. So it looks like all of our cases are now working. So let's go ahead and proceed with putting those back into the test suite. So we probably want to have this work for the old API. So I'm going to leave that one there. For the moment, there's probably a tidier way to achieve this. But we'll do it like this. I might tidy it up off stream afterwards. But at least that we've got the old using the old API, and then we can now update this one to use the new API. We're not actually using any of the lifetimes in the signature, so we should be able to do that. We'll do it like this for the moment. there's still a little bit of refinement needed in this new API. You can see that here, if I added the reference, it didn't actually want to compile yet. I think it will by the time we release, but there's a little bit of work to do there. So that now is okay. We should be able to go back to our tests module. And this time, if we run it, Nox is an automation tool for Python, which allows you to just run short scripts. It's very helpful. We've got lots of them in the PyO3 repository for different targets, such as running different example tests or this test suite. So we just updated this PyClasses file, and we can see that this code still works now that we've got the new API going. So I think what we'll do is we can start wrapping up the stream at this point. We've been going for 2 hours, and that's probably about as much as I'm going to be able to consistently keep talking for at the moment. Thank you very much for joining me today. I can see that we've currently got 10 people online. I'm not sure if you've been here for the entire stream or you've dropped in later. Your comments are very welcome to feedback. If you've got any questions at this point, maybe we can take some before we finish. Or indeed, if you've got suggestions on what you'd like to hear about. My plan is to really aim to do this weekly about the same time slot. If you're finding it interesting, or you have anything that you want in particular to focus on, I can look at those topics. Otherwise, the goal really is to take the whatever I'm working on PyO3 at the time and just turn that into something which we can talk about on stream. Also, a little bit of a plug. I as I mentioned at the beginning, I work Fridays on PyO3. That's not paid work to do. Primarily, it's from my own time because I believe that the ecosystem needs it. But if you find this valuable, I've got a GitHub sponsorship link, and every sponsorship really helps. It basically helps ensure that it's sustainable for me to keep doing this on Fridays. So if you want to put a vote into PyO3's development, then that would be greatly appreciated. Of course, don't give me any sponsorship money if you need that money for yourself. But if you would like to share some, it would be gratefully received. Okay, let's just finish then. What I'll do is I will put this as a branch, and let's push it to PyO3's repository as a draft PR. I'm probably going to tidy up a little bit this afternoon. I might add a couple more test cases and make it easier for fellow reviewers to see what's going on. But hopefully, at least then everyone can see the output of what we were just doing this morning together. So we can commit all that. We can support, we'll call the commit support. We'll push that up. And then if we go back to the web browser, here we are. So I'll go to pull request for PyO3. We've got this new one now, and I'll just create this as a draft for the moment. So let's say built on stream this morning. There's a little bit of tidy up to do later. This solves, and then let's just link back to, it was this PR which I was talking about. So we saw how PyType name didn't work. That's part of this diff. I'm basically introducing name for the new API, but didn't quite complete that implementation yet. So as promised, it will work. I copy link to that. So that was where we were going. Introducing some helper functions in and that will be good enough to at least label. For a lot of these API implementations, I'm normally quite careful about keeping the PyO3 changelog really up to date. So if we just look at the changelog, this is what's currently waiting to go for PyO3 0.21. And I like to have generally a description of what happened and the pull request numbers. I have to be honest that with the new API on Bound, I've been a bit forgiving about adding all those because there's so many pull requests which would have for basically add equivalent of old API for new API with just like one name changed or whatever, that really I think more on the PyO3 0.21 changelog, we'll just have to talk about how the new API has been introduced and the slightly different semantics it has, but say more or less that every API that existed before exists in the new API with just as minimal adjustment as possible. And the goal for PyO3 0.21 isn't to remove that old API. Instead, we want to have both in tandem for 0.21 so that you can do the migration without like immediately upgrading your crate and having a complete like meltdown in the Rust compiler errors. Amadurin says, I'm currently using PyO3 for creating performant Python libraries. Will really help if we can deep dive into profile and performance improvement of libraries using PyO3 to bridge with Python. So Amadurin, we definitely can. I could potentially show how I've been looking at Pydantic core, which is obviously something that I do the rest of the week as well. It's the Rust part of Pydantic and how we've been understanding the performance there. If you've got your own code, if it's public, actually, I could present that on stream if it would be valuable to you. We could explore your code base. If you like, there's I've got my email on the YouTube channel or on my GitHub. You could email me with your a link to your code, and I could maybe either dissect it live on stream straight up, or I could have a little look first if you wanted. If that's interesting to you, feel free to email it over. Otherwise, I can definitely look into doing that for a future stream for sure. Okay, so where were we? We were just completing. Oh yes, I was talking about the changelog and how. So for the moment, I'm normally quite strict on enforcing changelog entries, but I've labeled this as skip the changelog because, as I said, for these new APIs, there's so many little things that need to be tweaked. But really, as far as PyO3 users are concerned, it worked the same as it did before. You've just adjusted some types. And so there'll be a bit of a description about how to make that change in your own thing. But I don't want to litter the changelog with 150 or whatever different PRs that comment on the different pieces of it. So let's just push that on draft. So that's now up on the PyO3 repository. So if anyone wants to go read that code in full, there's not a huge amount in that diff yet, but we will clean it up a bit. I'll probably add some more test cases, and it's entirely possible. We have to test PyO3 for quite a lot of different Python versions and also for PyPy. And so sometimes one change that works for a given Python version doesn't work for everything. So I might have to do some manipulation of the pull request in more detail if, say, Python 3.7 doesn't work with it or something like that. But we'll see. So I think that's where I will wrap up. Again, thank you everybody for joining, and I plan to do this again next week. If you've got any feedback, either email me or you can reach me on Twitter, on LinkedIn, on Mastodon. I put all of those links are on my GitHub profile or on my YouTube channel. So do reach out if there's anything particular you'd like focused on. And take care. Have a good rest of your day.